What I'm excited to introduce is Shay Berkovich and Oren Ofer, and they're going to give their presentation right now. So let's buckle in and have a great session now, and of course, a great day. Thank you, folks.
Thanks. All right, thank you very much for coming, for joining. The next half an hour we'll spend talking about Kubernetes, attacks in Kubernetes, and what we think constitutes effective detection in Kubernetes and cloud-native environment. Let's start. My name is Shay Berkovich. I come with the software development environment background. I have, fun fact, I hold Masters of Science in Runtime Verification of all the things from University of Waterloo. But 12 years ago, I started coding for WAF, and I got into the AppSec. And 12 years later, I'm here working for WIS threat research team. And since then, I stopped being a software developer and started being a security researcher. And with me today is Oren Ofer.
Hi, everyone. Excited to be here. My name is Oren Ofer. I've been practicing detection engineering at Runtime Sensor in the past 8 years, working on Windows, endpoints, cloud, Linux, and naturally Kubernetes clusters. Prior to that, I'm coming from a background of penetration testing and red teaming, and now transferring that hacker mindset to the detection engineering field. So happy to be here. Let's go.
Let's do this. So what can you expect from our presentation? Well, we'll start with the intro, motivation, attacks in Kubernetes, the evolution of attacks. Then we'll start with the sources. We'll start with starting with the audit logs, Kubernetes audit logs, and then finish with the runtime sensor. Then we'll present the actual demo based on real attacks that we observed, and we'll analyze that demo, and we'll think together how we can detect the full attack. And then we'll conclude with the final pitch about combining sources, what constitutes effective detection in our opinion in Kubernetes. All right, so we promised there's not going to be LLM models in this session, so that's a relief. We'll talk about Kubernetes attack chain first. Kubernetes is a complicated beast. It has its own ecosystem. It has its own security domain. We talked about it extensively in Kubernetes security report. But for purpose of this talk, we can simplify this, right? Because it's still a system. Attackers still attack it, starting with the initial access. Then there are multiple iterations of lateral movement, privilege escalation, perhaps cloud pivot, and then finishing with the impact, either local or global. So let's keep that attack chain in mind. And let's talk modern attacks. What can you expect from them? So we've seen several worrisome trends in the field, starting with the cloud component. Attackers know cloud at this point. All the recent incidents, including the gem security recent incident that they described, we saw that attackers are proficient with cloud APIs, and they use red team tools like Priorities and Pacu. So that's new, not new for them at this point. There are also new initial access vectors. So if we take, for example, Team TNT, they started with looking at the exposed Docker API sockets, but then moved quickly into RCs for WordPress plugins, Postgres misconfiguration, and abusing the leaked cloud creds. And finally, there's this trend of adoption of all techniques. Our sensor research team has recently observed what they dubbed PyLoose, which is in-memory execution of the crypto miners with Python. And by itself, it's not new, but the application is new. So we see those three worrisome trends: adoption of all techniques, cloud component, and the multitude of initial access vectors. And by the way, if you want to know more about this, I gave recently talk in the KubeCon in Paris about the various initial access vectors in Kubernetes, and there are a lot of them. So these trends, they kind of make it hard on the SOC, right? Because now SOC needs to be an expert in everything. So us as defense team, we need to ask ourselves, okay, how can we help SOC analysts to actually be successful in this in modern cloud landscape scenario? So we believe that the solution for effective detection is multi-domain. First is it's the temporal domain, so like tracing the attack chain. And the vertical axis is the abstraction levels and combining multiple sources for detection. So let's talk about those sources. What kind of sources do we have? Starting with the sensor, which has visibility on the kernel level host containers. Then we have on the Kubernetes the admission webhook and audit logs. And for the cloud, we have, of course, cloud detection feeds, logs, VPC, etc., and more. So let's talk about those. Now, as a metaphor, we'll use cluster as a business, which we want to secure. So first, we start with the Kubernetes audit log, and which we compare to CCTV system that can detect some malicious activity inside the business. In terms of architecture, Kubernetes audit log is part of the master node, and it's controlled by a Kubernetes API server. The format of the events is as follows. So this is not the full event, but this is how it looks, and this is vanilla Kubernetes audit log event. It has the three pillars: username, the principal, in this case system anonymous, the verb, list, and the resource, pods. So we know that system anonymous has listed pods in default namespace. So this is something that you probably want to detect. This is Azure. This is AKS, managed cluster. The original event is now in properties.log field, and then there's a metadata, but it's still retrievable. It's still okay, and they add another time step. I don't know why, but I guess it's okay. We can work with that. And this is GKE. As you can see, the format is completely different. So yes, they do change format into their proprietary format, which brings us to the gotchas of audit logging in managed clusters. So first of all, they're not all on by default. Only in GKE, the audit log is on by default. In terms of medium, where you can retrieve those logs, it's CloudWatch. It's different everywhere, of course, Event Hub in AKS, etc. So you need to know that. And finally, audit logs, audit options are unknown. So audit options is actually the file that tells to the Kubernetes API server what to log, which events to log and which events not to log. And you can't control it in managed clusters. It's controlled by cloud vendors, which might be a problem if you want full control over your clusters. In that case, you need to use self-managed clusters. And of course, proprietary format in GKE, which means you either maintain various rule sets or you need to normalize the events. Basically, it's non-trivial. Now, the volume of the logs can get very big, very fast, and noise reduction is critical in this sense. You might want to monitor only interesting actions. So, for example, get, list, watch. Unless it's a secrets, you probably are not interested in those. We recommend to weed out control plane principles. So in this case, we remove all the principles starting with the system, except system anonymous or system service account, which kind of makes sense. Or you can just exclude non-interesting principle, like Prometheus server, that are known to be noisy. So that's some of the methods to reduce the noise. Now let's do a short rule trivia. Who knows what does this rule detect? Anybody? So for the background, this is Rago on GCP event JSON. And the key here to see, like some of the hints, we have create. The event ends with create. The granted is true. And we see the anonymous and unauthenticated in principal email, which means that this is a resource created by anonymous principal. So this is something that you probably want to detect. It's high severity in my view, which potentially hints that your cluster has unauthenticated mode enabled. Now, audit log can't do everything because there are blind spots. As we said, it's controlled by API server, so it can only see what API server can see, which means all the local operations on the worker node are not visible. Okay, so things like static pods, direct socket API, RCs in data plane, Kubernetes audit log won't see those. Okay, now let's talk about admission webhook. Traditionally, admission controller is thought as an enforcer, right? But in our case, we don't need to use it as enforcer. We can use it in the audit mode, right? So we define it. You can define the mutating or validating webhook, in the audit log and just collect those events. The thing is, those events are state changing in the cluster. So in terms of coverage, there's less coverage than Kubernetes audit log. And then you might ask ourselves, like, okay, so why are we talking about is there's less coverage? So like, why won't we just use Kubernetes audit log? Well, the thing is that, first of all, there are cost savings associated with less events, of course. And you have full control over what you monitor because you define the configuration of that webhook. And it assembles, collects the events that you're interested in. And it's cloud agnostic. So you don't need to maintain multiple rule sets, okay? So this is option. This is how the event typically looks like. It's called admission review because that's admission webhook. But it's a bit different than the Kubernetes audit log, but it has the same components. It has the principal operation, create in this case, and the resource type, cluster role in this case. So you have kind of still basic information to create detections around. We would advise to start with stars, which means just monitor everything, give me everything that you can, and we'll go from there. And to reduce noise, you can focus on certain resource types, for example, pods, monitor only pods, monitor only create pods events. You can start with that as well. Another noise reduction is just weeding out control plane principles or actions. So in this case, we're ignoring the namespaces kubesystem and kube nodeless. And for the rules trivia, we have here example of the which event, by the way? Anybody knows? So the key here is connect. Connect, it means kubectl exec. So we probably don't want to this is probably not the high severity, but it could be high severity in combination with other events. We still probably want to know that somebody executed into the pod in the cluster. In terms of blind spots, same blind spot as Kubernetes audit log. In addition, there's no impersonation information if somebody impersonated. The get, list, watch verbs are not there. As I said, there are only state changing events there. And the denied requests are invisible because the webhook happens after the authorization and authentication. So all those failed attempts are not visible in this case. Okay, to the cloud logs, which I think of as a neighborhood CCTV that helps to detect that the getaway car after the burglary. So to put kind of events together and what happened and where the burglars disappeared. So there are quite a few cloud logs. We're not going to get into too many of those, like DNS queries, VPC logs, etc. The two main ones being cloud audit log, like CloudTrail, and detection feeds. So there are actual vendor detection feeds like SCC, GuardDuty, and Defender for Cloud that you can use. There are Kubernetes rule sets in them, like privileged container detected. I mean, you can implement them with your own detection, or you can use this one. Of course, there are costs associated with them. So another option that you can do, you can just use that as enrichment and Kubernetes perimeter monitoring for your bigger detection solution. So I'll explain what I mean by enrichment. Enrichment is when we want to know additional information. For example, about acting principle, history, what they did, other actions they did in the cloud, privileges associated, perhaps leaked credentials. Same about origin IP, history, reputation, geolocation, subject resource information. If something happened in the pod, who started this pod, who's the owner, sensitivity associated with this pod, resource privileges, and perhaps even security finding, right? All this information gives us additional picture. So we're not going to go into the rules trivia with this ones. I just put this snapshots to show the complexity of the cloud rules. And the use case here is the monitoring of the Kubernetes perimeter. So in this case, series of YAM enumeration attempts originated from an EKS container, and this one is MDS connection in an EKS worker node with high privileges. So that means that we are interested in the events that happened from the Kubernetes reaching to the cloud API logs. Those are interesting events that monitor the perimeter that might symbolize the pivot point. Okay, and I'm passing the baton to Oren, who's going to talk about Agent Smith.
Okay, so our runtime sensor is our agent with the boots on the ground, or the cluster, if you will. So no need to squint your eyes there. This is not the Star Wars intro subtitles, even though we just passed the May the 4th. This is the extensive MITRE ATT&CK framework, which extensively details the attack lifecycle and breaks it down into attack tactics, techniques, and procedures into single steps. And the runtime sensor plays a crucial role in highlighting and monitoring those events. So it does so by employing behavioral monitoring of application users from the containers themselves up to the node and host itself. It monitors for any deviations in standard patterns to identify anomalies and suspicious activities. And it does so by monitoring specific events, and we'll go to some examples soon. The runtime sensor also have a crucial role in collecting and extracting crucial data for detection that can be integrated with third parties like threat intels, collecting IOCs, or streamlining these events to our Blue Team SIEM, and they're correlating with additional detection tools. Another important functionality of the runtime sensor is providing with prevention and response capabilities. So once we identify something suspicious that looks like an attack, it can automatically kill the process, kill the container, block network connections, and more. And when that happens, the runtime sensor can also help us by collecting forensics package that will help the Blue Team to investigate the source of the breach, or maybe there was a lateral movement and where we need to keep our investigation going on. So how do we get that data? There are several instrumentation tags. I am listing here the prominent ones, and some are being used from the user mode by placing hooks on user mode functions, or debugging the process as it runs and inspecting its arguments on each execution. There are technologies that utilize kernel module. Kernel module can inspect and place hooks on system-wide events like system calls and monitor internal structures in the kernel. But we do expect to see in Kubernetes environments the usage of the eBPF technology, which kind of benefits from both worlds of the user mode and kernel mode. It can place hooks on both, and on the same while enjoy the inherent protection of that technology that safeguards us from not impacting the worker node functioning properly. So what kind of events we would like to instrument? So starting with the process and thread, as soon as the process starts, the runtime sensor can collect a lot of information, such as information about the binary, which will be used to calculate its hash and help us identify malware with known malwares. And it can collect command lines to provide us with simple and yet effective detections of LOL beans abuse, and a lot more data. So next, we would like it to collect file events that will help us to detect credentials access. It will help us to detect privilege escalations and persistence activities. Next, we would like it to collect network events. We would like to get information about the local and remote endpoints, about DNS queries, or usage of raw sockets, and that will help us to detect connections to miner pools, connections to C2s, etc. Next, we would like this runtime sensor to monitor memory events. By monitoring memory events, we know that hackers like to do evasion techniques and hide their payloads in memory. They use memfd, SHM, and other techniques. So that will help us identify files and in-memory payloads that were decoded there. Next, we would like to have a runtime sensor monitoring the discovery, load, and unload of user or kernel modules. That will help us identify rootkits, which will help us identify any process execution hijack flows and additional shenanigans. The runtime sensor could benefit from also collecting information from the Linux audit logs. The Linux audit log stores informations about activities of services and daemons and applications that are running on the system. So that, for example, we could gather information from there and detect SSHD printouts that would indicate brute force attempts and password guessing attempts. Also very important, the runtime sensor can collect information from the container runtime itself. And by that, it can match the information of running processes and match that to the processes that are coming from the image of the container and help us identify any deviation. We know that hackers like to install their own tooling, so that will help us to identify the container drift problem. So how do we get our sensor? So we will aspire to have our sensor on every worker node. For that end, we can utilize the Kubernetes daemon set deployment. That deployment types ensures that we will have our runtime sensor pod on each worker node, with the exception in managed environments for the master node. And that takes us to some considerations. So as said, one of the cons is that we cannot deploy it on managed nodes. It's a given state. Another con would be a proprietary application context. For example, in some organization environment, the application does accesses for its benign and normal operation some sensitive files. And I argue that it's not entirely a con, because this can generate a productive discussion to identify why the application needs to access that sensitive file. Can we do it otherwise? And if it is that the way that we should operate, we can also allow at least that operation. Another con, the sensor theoretically can access Kubernetes and cloud context, but that would not align with the best practices, because that would require applying high permissions to the sensor, and the sensor would have to utilize a lot of the network to extract all those traffic. And so that is not necessary, as we can get that traffic, that information elsewhere from the sources that Shay mentioned earlier. Okay, so on with the demo. We prepared a demo that is based on real events, funny to say that in a movie theater, and that we have seen at our customer base. The initial attack access vector is a Jupyter notebook that is offered as a free service from some vendors. So let's start. So as soon as our attacker gains the access to the Jupyter notebook, he installs some tools, including kubectl, and starts by interrogating the cluster. So using the auth-scanI command, the attacker quickly realizes that he has very high permissions on that cluster. He continues to find additional useful insights about the cluster, like identifying the namespaces that are available, and also looks for any Kubernetes secrets, but that not yield anything interesting. So at this point, our attacker decides to deploy a crypto miner in the environment. Let's see that. Okay, deployment XMRig created. So our pedantic attacker at this stage would like to verify that his XMRig is up and running, so he issues the get pod command. We can also see here the Jupyter notebook that he operates from and the new XMRig pod. Now, our attackers are greedy. They would like to furthermore escalate and pivot into the cloud. So they search for pods that are associated with the EKS pod identity, rather new feature introduced by Amazon, and they identify the bucket reader pod. So they issue a command into that pod, a kubectl command, to cut the file that contains the token of the EKS pod identity. Now, using the EKS pod identity, they are now generating AWS API token. Now, I would like to state that from this stage, having AWS API token, valid token, they could continue and carry out the attack from any machine in the world. It doesn't have to do that from inside the cluster, but for the sake of the demo, we will continue to show it from here. So, using the AWS token, our attackers are now creating S3 session, and they now are validating that the session is live and valid by getting the ARN. Next, the attackers now list the first bucket. Now they are able to download files from the buckets, extracting some sensitive data, successfully completing the attack. Back to you, Shay.
Thanks, Oren. Okay, so let's talk what we've seen here. Okay, we'll spread it into the stages. So we started with initial access via Jupyter Notebook, right? If we think about the detection sources, how can we detect it? Well, not really. Only sensor really sees the attacks that executed on the pod, but those attacks probably seem benign. So that's a tricky one. Okay, moving on to the local kubectl install. This one is visible on the VPC flow logs and probably DNS query as well, and the sensor will see that. Okay, so that's better. Moving on, permission enumeration, right? That kubectl auth cani command, that's invisible on cloud, on sensor, because that's API call to the Kubernetes API server. And so the best one to detect this would be Kubernetes audit log. Okay, and so on, we're moving on with those stages, building the full picture of the attack, and finishing with the creation of the session and reading and enumerating the buckets, the S3 buckets, right? And when we think about that one, the last stage, it's only visible on the cloud, actually, because that could be run from any IP, right? Because the previous stage was still in AWS credentials, copy-paste, and then run it from some kind of C2 server or something like that. And another point, there's a new, that action is actually executed with another principle. So how to connect all those stages, that's the tricky part, and it's a topic for another session on BSides, but it's possible. It's possible if you have, there are a couple tricky stages that you need to connect to get the full view. It's possible, but you need the good medium that can express that logic. So for example, in the last movement from stealing AWS credentials, you need to realize that, okay, the EKS pod identity file was accessed, and that file actually points at that role. So that's our connection. And then the next minute, that role was active, perhaps from another country. You need to put this together. Okay, and that brings us to the final slide of this presentation, which basically I think the most important slide, that if you want to take away something, that's the one. So we believe that effective solution for effective detection is multidimensional. The x-axis is the temporal. We want to know all the attacker actions starting with the initial access through lateral movement, etc., finishing with the cloud pivot. And the vertical axis is cutting through the abstraction levels from the kernel, CRI, Kubernetes context, cloud context. We need all of that. And coupled with the noise, very smart noise reduction for cost concerns, but also false positive reductions, all those together will bring us closer to the effective detection in Kubernetes and cloud native ecosystems. And that's all we had for today. Thank you so much.
Let's go round a hand. Thank you, gentlemen. I think we've got time for one question for folks at person called Anonymous. What are go figure, right? What are the most common types of false positives you guys have been seeing with Kubernetes detections?
Well, it depends on the source. Depends on the source. It could be it doesn't have to be false positive. It could be benign, but you need to know which one is benign and which one not. So there are different types of false positive depending on the source. I guess we can't go too far into those. Even that kubectl exec, it could be false positive.
Well, that makes sense, yeah. Thank you, gentlemen. We've got some gifts for you here, care of our friends at Socket Security. Give a round of applause again. For here you go, Oren and Shay. Gentlemen, thank you very much for your time.
Thank you very much.
Folks, thank you for coming.